This question is from GATE Mechanical Engineering 2019. This is question number 24 of set 1. The question is, air of mass 1 kg initially at 300 Kelvin and 10 bar pressure is allowed to expand isothermally till it reaches a pressure of 1 bar. Assuming air as an ideal gas with gas constant of 0.287 kilojoule per kg Kelvin, the change in entropy of air in kilojoule per kg Kelvin rounded off to 2 decimal places is. So we need to find the value of change in entropy of air. For ideal gas, Gibbs equation can be written as Gibbs equation. So for ideal gas, we can write the Gibbs equation as T ds is equal to du plus p dv. Let this be equation number 1. And the second Gibbs equation can be written as T ds is equal to change in enthalpy minus v dp. Let this be equation number 2. Now here in the question it is given that the process is isothermal, right? So for isothermal process, let's write here, for isothermal process, change in temperature is 0, delta T is equal to 0. Therefore, the change in the internal energy of the system will also be 0. So du is equal to 0. Now for ideal gas, from the ideal gas equation, we can write PV is equal to nRT. That's what we know from ideal gas equation. So we can write pressure into volume is equal to mRT. Here R is the gas constant and not the universal gas constant, right? So the relation between R gas constant to the universal gas constant, this is R bar is divided by m, and m is the molecular mass. Okay, so don't confuse with it, because we also have the relation PV is equal to nRT. So that time we are using actually n bar here, like PV is equal to nRT. Okay, so here n is number of moles. Now here, if we can also write it as PV upon m is equal to RT. Now this is the specific volume, so we can also write it as P is equal to, I'm writing it as specific volume, that is volume per unit mass. So I'll write it as small v. Okay. Now let's move ahead. Now using this relation and du is equal to 0, we can write this, the first Gibbs equation as T ds should be equal to du is equal to 0. That's why now P into change in volume, because this is change in specific volume actually. Now let's substitute this P from this relation. So we can write T ds is equal to RT by specific volume into change in specific volume. Okay. Further, we can also write this equation as ds is equal to RT by T, that will get cancelled out, dV upon V. Now let's integrate this equation from state 1 to 2, right? From state 1 to 2, that is isothermal state. Isothermal. So at state 1, now if we integrate it, so at state 1, let the entropy be S1, and at state 2, let the entropy be S2, because we are integrating it from state 1 to state 2. And here, let the specific volume be V1 and specific volume here be V2. Now this integral, this will become change. Now if we integrate it, it will become S2 minus S1, that is equal to R is a constant, and the integration of 1 upon V is log V or ln V, natural logarithm. So ln V2 minus ln V1. Okay, and this change in entropy, delta S2 minus S1, we can write delta S is equal to R into ln V2 by V1. Now let this be equation number 3. Now we are given the process is isothermal, right? So for isothermal process, so for isothermal process we can write P1 V1 is equal to P2 V2, because PV is equal to nRT. If we suppose this, then here R is constant, N is constant. Even if we write PV is equal to mRT, so for a particular gas this R value will remain constant. Here it is universal gas constant, so it will always remain constant. And for isothermal process the temperature is also constant. The number of the mass also remains constant here, right? So only varying quantity is P and V, that is pressure and volume. So we can write P1 V1 is equal to P2 V2. So from here we can write V2 by V1 is equal to, this will become P1 by P2. Let this be equation number 4. So now let's substitute this equation number 4 in this the change in entropy relation, that is equation number 3. So what we will get here is, let's write it here. So delta S, change in entropy, will be equal to R ln P1 by P2, right? Now we know the value of R, that is 0.287 given in the problem, ln, and P1 by P2, P1 given is 10 bar and P2 given is 1 bar, right? So it is ln 10. Delta S, that is change in entropy, will be equal to, if you use the calculator to calculate this value, you will get 0.66084 kilojoule per kg Kelvin. And this is our final answer. Now let's go back and fill the blank. The change in entropy of air is, how much just we calculated? 0.66084 kilojoule per kg Kelvin. To get more information on entropy change in closed system, to learn more about entropy, you can follow the NPTEL lectures of entropy change in closed system by Professor Suman Chakravarti of the Department of Mechanical Engineering, IIT Kharagpur. Hopefully I was able to solve your doubt. Have a great day.